Right, we're going to look at a little technique for solving exponential and logarithmic equations, and it's going to use the fact that logs and exponential functions are one-to-one. For the exponentials, you need to have the same base, and for logarithmics, you also will need to have the same base. So let's do an example here. And I have log base 2 of x plus 5 equals log base 2 of 3x plus 2. So we have a log equals log, and we have the bases are equal to, or the bases are the same. Since logs are one-to-one, and it has to have the same base, then we can equate the arguments inside. So the inputs have to be the same because the outputs are the same. Alright, so if I solve this, I'm going to subtract 2 from both sides. I'm going to subtract x from both sides. And we'll divide by 2. Since logarithms have domain restrictions, the argument inside a log has to be greater than 0. We need to check for logs. I'm going to check 3 halves. So we're just going to replace the x's with 3 halves. Okay, on the left I get 6.5. 3 over 2 is the same thing as 1.5. 1.5 plus 5 is 6.5. On the right hand side, 3 times 3 halves will give me 9 halves. 9 halves is the same thing as 4.5. And then 4.5 plus the 2 here will give me 6.5. So we do have equality on both sides. So this is a good solution. Try another one. Okay. This time they didn't say what the base is, so the base is understood to be base 10. So the base is the same. The outputs are the same, log of 3x and log of 130 minus x squared. Those are both y values. If the y values are the same, that means they came from the same input. Okay, so we can go ahead and equate the arguments inside. That's the input. Okay, this is a quadratic, and usually we solve this by quadratic formula or factoring, and we need to set one side equal to 0. What I want to do is I want to add x squared to both sides and subtract 130 from both sides, because that's going to make the factoring easier. So I'm going to add x squared to both sides, and then I'm going to subtract 130 from both sides. And then we're going to look for factors of a negative 130 with a sum of 3. So that happens to be 13 and negative 10. Okay. So I'm going to get 2 solutions, which is fine, but I need to double check to make sure both of these work, because logarithms have domain restrictions. So if I'm getting a negative inside the logarithm, that's no good. So if I check x equals negative 13, I notice that it's not going to work, because in the first one is log of 3x, and if I plug negative 13 in, I'm going to get log of negative 39, and that's not in the domain, so that's undefined. Give yourself a sad face if it didn't work. And then we'll try log of 10, so we'll plug it in and see if we get the same thing on both sides. You get log of 30 equals log of 130 minus 30, which is 30. So that looks good to me. So we have one good answer at least. Right. So those are log equations. If you just have a log equals a log, same base, equate the stuff inside. With exponentials, they needed to have the same base, and then we could equate the exponents. So 3 to the 2x plus 5 is equal to 81. 81 is the same thing as 3 to the 4th, so we can get the same base. Once we have the same base, we can equate the exponents. And you can go ahead and check the solution if you want, but for exponentials, the domain is all real numbers, so we don't have to worry about any domain issues. So we're okay with exponentials. Okay. Let's look at e to the 3x equals e to the 130 minus x squared. Got the same base, so we can equate the exponents. And hey, look, we just solved this problem, this quadratic. We'll solve it the exact same way. All right. Now both those solutions are going to be good because the exponential's domain is all real numbers, whereas the logarithmic's domain is 0 to infinity, so we can't take negatives for logarithmic equations. However, for exponential, we're all right. All right. Let's look at a couple of examples where we use the definition of log to solve. So first one will be some exponentials. And we're going to actually use our calculator. We have two buttons on our calculator that will do log base 10, which is the common log, and then ln, which is the natural log. So 10 to the x is equal to 32. So if we put that in logarithmic form, it's going to be log base 10 of 32 equals x. And remember, log base 10 is the same thing as just the log, that's common log. And I'm going to need my calculator, so I'm going to have to plug log of 32 into my calculator. And then I'm going to round it to 4 decimal places. And I think that's typically what my math lab wants, or maybe the textbook says they want 4 decimal places. You know, maybe on a quiz or a test we might ask for less. It just depends on the instructions. But from what I've seen from my math lab in the textbook, they usually want 4 decimal places. Okay. For b, we'll have 15e to the x equals 29. And one of the big common things for logs and exponentials is we need to isolate them. So the exponentials e to the x, we need to isolate it. 15 is attached to it by multiplication, so we need to divide both sides by 15. And it's best not to do any rounding, so just leave it as 29 over 15 for now. Alright, now we can write this in logarithmic form, so it's going to be log base e, 29 over 15 is equal to x. But remember, log base e is the same thing as the natural log. And I need to put it in the natural log form so that I can use my calculator. At some point in time we'll learn change of base formula too, so you'd be able to use the change of base formula to find this also. Alright, and then same deal, use your calculator and round to 4 decimal places. Okay, I have one more kind of fun problem, and then it looks crazy, but it's not so bad. So we're going to solve log base 3 of log base 5 of log base 2 of x, and that's going to equal 0. So right there you just said, oh, what in the world's going on? I have no idea. Well, just follow your definition of log. Alright, so this stuff in here is just a number. Okay, could be 5, who knows? So we're going to use our definition of log, so 3 to the 0, base, exponent. So base exponent is equal to the argument inside the log, which is log 5, log 2 of x. 3 to the 0 is 1. And then we'll play the same game again. Log base 5, exponent of 1 is equal to the stuff inside. The stuff inside the log is this log base 2 of x. So 5 to the first equals log base 2 of x. And then we get to do it one more time. Log base 2, so the base is 2, exponent is 5. And that's equal to x. So, it wasn't so bad. That looks crazy, but it wasn't so bad. Alright.